Hello and welcome. This is SPPP 1042 or SHPP 1042, University Technology Malaysia Introduction of Education Technology course. This is the 7th class in the second semester 2020. In this class, we are going to talk about computational thinking, CT, and its relation to education technology. I actually took this course years ago and I was confused about the actual meaning of CT and how does it relate to education technology. I hope I answer this question for you in this class. This class discussion outline as follows. Firstly, we are going to explore various definitions of CT, and then why do we actually need CT in our daily basis. And then we are going to go through common problem-solving process, following by CT key concepts, techniques, such as decomposition, pattern recognition, abstraction, and finally, algorithms. So what is actually computational thinking? There is a quote for Janet Wang that says, computational thinking is a fundamental skill for everybody, not just for computer scientists. For example, in reading, writing, arithmetic, we should add computational thinking to every child's analytic ability, which shows the importance of CT to everybody, not only for the experts in the field of computer science. We need to teach CT for our childs in all aspects and fields. So what do we actually understand when we hear the word or the term computational thinking, CT? We can simply define it as an approach. It is an approach to problem solving. How? Actually, CT depends on breaking the main problem into smaller problems or smaller chunks, and then solve each of these problems aside. By doing so, you are actually solving the main problem. So it's a solving problem approach, which simply means you are going to break down the main problem into smaller problems and solve each of these small problems, and then by doing so you are actually solving the main problem that you have. So from the previously mentioned definition of computational thinking, it is actually a way that could simplify any complex or messy problem so that a human or computer can understand. So according to BCS 2014, computational thinking skills are a set of mental skills that convert complex, messy, partially defined, real-world problems into a form that a mindless computer can tackle without further assistance from a human. So it's all about simplifying the problem, providing solutions. When you talk about CT, you are talking about simplifying a complex problem into, or maybe we can say, breaking apart the big problem to provide a solution. So CT actually allows us to take a complex problem, understand the real problem, and then develop solutions. By doing so, we can then present these solutions in a way that whether a computer or a human can understand, or both of them. So CT is actually very important and essential to the development of computer applications, but it can also be used to support problem solving across all disciplines. As we mentioned in the beginning of this course, actually CT, it's not only for computer scientists. No, it's for all disciplines, all curriculums. So students, for example, who can learn CT across the curriculum can begin to see the relationship between subjects as well as between the school and real life. They can relate school to real life situations. CT actually make the student think critically. They could relate whatever subjects, whatever situations, whatever circumstances they go through in school, and then link it to their real life situation. So from all the above, that we can simply say that CT is a problem-solving process that includes a number of characteristics, such as logically ordering, analyzing data, creating solutions using a series of ordered steps or algorithms, and disposition, such as the ability to confidently deal with complexity and open-ended problems. So actually, CT is all about simplifying complex problems that face whether a human being or a computer, and then analyze this problem, develop solutions, and then you know ending this whatever problem that they face. So the question is now, why do we need CT in our life? And is CT actually only for certain kind of scientists or some? The question is, we need CT for all disciplines. It's not only for, as we mentioned in the previous slide, it's not only for computer scientists. No, it is very important and essential for all disciplines to support problem solving. And as we mentioned before, students who can learn CT actually across their curriculum can begin to see the relationship between their, the subjects that they are learning, between their school and outside of the school. They can relate any situation or any circumstances they face to the school and to their subject and to their education and learning teaching. So actually CT is not only for computer technology and computer scientists. All right, great. So similar to any problem or any process, common problem solving process actually consists of 7 steps that we need to be aware of. Firstly, we need to define the problem. What is the problem that we have? And then we need to analyze this problem. Analyze this problem actually means that we are going to break this problem down into small parts to make it easier for us to develop a solution. All right, and then determine the criteria for optimal solution. We need to be aware of our criteria for the proposed solution. And then we are going to propose solutions. We are going to propose actually more than one solution, and then after proposing the solutions, and then we are going to evaluate the proposed solutions to make sure that one of these solutions is actually going to work. And then select this solution that we already evaluated, and then suggest the strategies to implement these solutions. How we actually going to make it work. we need to suggest these strategies to the implementation of this solution. This is actually a very simple explanation of how we commonly solve problem. This is the common problem solving process. All right, lovely. So moving on to more definitions to CT. These actually two associations that have defined CT, which are ISTE, which stands for International Society for Technology in Education, and Computer Science Teacher Association. They have defined CT as a problem-solving process that includes the following characteristics, and it's not limited to the following characteristics, but it needs to be included. Firstly, we need to formulate our problems in a way that enables us to use computer and other tools to help solve them. How we are actually going to do that? Formulating the problems means that we need to use computer language. We need to be aware of computer language before we convert our problems into actually, for example, codes or any computer language that makes actually the computer understand this problem. So we need to formulate our problem in a way that the computer would understand this problem, and this actually formulation needs to be logically organizing, and if we have any data, then we need to analyze the data correctly. And then we need to represent data through abstractions such as models and simulations, and we are going to talk about that later in the end of this class. Following by automating solutions through algorithmic thinking, and we are going to talk about algorithms at the end of this class as well. And then identifying, analyzing, and implementation possible solutions with the goal of achieving the most efficient and effective combination of steps and resources. And finally, we need to generalize and transfer this problem-solving process to a wide variety of problems, which simply means, all right, we have solutions now for any kind of problems. Then we need to generalize. We need to use these solutions for any other similar problem. It's not actually a one-step process. No, we need to use it, transfer it, make use of it, so that we can, get the best of this problem-solving process. All right, so now we are going to talk about computational thinking key concepts. We actually have 4 key concepts that we are going to talk about, define, and have some example of it, which are decomposition, pattern recognition, abstractions, and algorithms. All right, so computational thinking actually involves, as we mentioned in the previous slide, the key concepts of which actually involves these 4 definitions or terms. Let's read this slide and understand one by one. All right, so CT actually involves taking any complex problem, as we mentioned, and then breaking it down into smaller, easier, more manageable problems. This process is actually called decomposition, which is the first key concept. All right, so what is decomposition? Decomposition is the process of breaking any complex problem into small parts more easy parts, more manageable problem, and then solving it. All right. Each of these smaller problems can then be looked at individually, considering how similar problems have been solved previously. All right. We have smaller problems now. We need to look how other people have solved this problem. If they have similar problem with this problem that we have, this is called pattern recognition. We actually recognize what are the patterns that other people previously used to solve the same problems we have. All right, following by focusing only on the important details while breaking the complex problem into smaller parts. We need to focus only on the important details while ignoring irrelevant information. This process is called abstraction. We actually abstract any irrelevant information, any, not so important details. This is called abstraction. Okay, and then we have simple steps or rules to solve each of these problems. How? By doing the algorithms. So decomposition, pattern recognition, abstraction, and then solving these small problems by using algorithms. And then finally, automation is the ultimate step in computational thinking that can be implemented through computing tools. So this is actually the whole process of CET and what actually CET does involve. All right, great. So once again, what are the key techniques to CET? Decomposition, pattern recognition, abstraction, and algorithms. We need to break down the complex problem or the system into smaller parts that are more manageable and easier to understand. This is called decomposition. And then we look for similarities among and within problems that can help us to solve more complex problems more efficiently. This is called pattern recognition. And then we move on to abstraction. We need to focus on the important information only. We ignore any irrelevant details involved. We filter out the characteristics that we don't need in order to concentrate on those that we do. And then finally, we develop a step-by-step solution to the problem or the rules to follow to solve this problem, which is called algorithms. This is actually the main key techniques to CT that we need to understand in order to understand the whole meaning of computational thinking. Okay, great. So now let's go and see some of the example for decomposition. So decomposition in practice, we actually do many tasks in our daily basis without even thinking about or decomposing it. For example, if you want to brush your teeth, this is actually the main problem here. To decompose the problem of how to brush your teeth, you would need to consider, all right, do you have a toothbrush or do you have a toothpaste? How long to brush your teeth for, and how hard to press on our teeth. This is actually breaking the main problem, which is brushing our teeth, into smaller manageable parts. All right, this is one example. The second example is, for example, solving a crime. Okay, there's a crime, and then to solve this crime, it can be very complex problem as there are many things to consider. solving the crime itself is a complex problem, but if we break this complex problem into smaller, more manageable problems, then we could save it easily. For example, a police officer would need to know the answer to some questions, all right? And then what crime was committed, what time, when, where, and then if there's any evidence, if there were any witnesses, if there have recently been any similar crimes. So the complex problem here is the committing the crime, but now it has been broken down into simpler problems that can be examined individually in detail. So decomposition, once again, is breaking the complex problem into more smaller manageable problems. And as we mentioned before, actually we do many tasks on a daily basis without even knowing that we are actually decomposing our problems. All right, second, pattern recognition. Pattern actually exists among different problems and within individual problems as well. For example, to find patterns in problems, we look for things that are in common, you know, which means the same or very similar in each problem. It may turn out that no common characteristics exist among problems, but we should still look. For example, in math or physics, we could solve many questions by using the same equation. This is actually one of the pattern recognition, and the equation have been invented previously by other people. So we are actually using their solving problem to solve our problem. This is actually the real meaning of pattern recognition. All right, more example for you to understand the meaning of patterns. Let's assume that we want to draw a series of cats. All right, we all know that all cats have common characteristics. As we mentioned, patterns means common characteristics. All right, so among other things, that all cats have eyes, tails, and fur. They also like to eat, for example, fish and make mewing sounds. Because we know that all cats have eyes, tails, and fur, we can actually make a good attempt by drawing a cat simply by including these common characteristics. Because we know all cats have these common characteristics, we have a good chance to draw our own cats. All right. So once we know how to describe one cat, we can describe others. This is the meaning of patterns. Defining one element, all right, could be the same definition of other elements, common characteristics. Okay, but the only things that are different are the specifics, which are not important here. For example, some of the cats might have green eyes, some might have blue eyes, long tail, black fur. Another cat may have, for example, yellow eyes, short tail, and so on. So patterns actually the things that are in common characteristics. All right, so we have two types of patterns here. Firstly, patterns among different problems, and then patterns within the problem itself. All right, let's see this first type of patterns among different problems. Okay, let's take cake, for example. We want to decompose the task of baking a cake. All right, Decomposing mean we would highlight the need for us to know the solutions of series smaller problem. For example, what type of cake do you want to bake? What ingredients do you want to add? How many people do you want to bake the cake for? How long we need to bake the cake for, and so on. These are the decomposition of baking cake process. Okay. So once we know how to bake one particular type of cake, we can see that baking another type of cake is not that different. For example, each cake will need a precise quantity of specific ingredients. Ingredients will get added at specific time. Each cake will bake for a specific period of time, and so on. So, to make it more easier for you to understand, patterns among different problems. For example, today I would like to, bake a chocolate cake. I would do the same all procedures, but I would add chocolate. Alright, tomorrow I would bake a vanilla cake or a strawberry cake. So I would remove the chocolate, add vanilla or strawberry. So this is actually the same. I would follow the same technique, the same procedure for both chocolate and whatever other flavor. So this is called the among different problems. We use the same procedure, the same techniques, but there's one particular type, one particular thing that we need to change. This is called patterns among different problems. Let's see pattern within the problem. Okay, so patterns within problems may also exist within the smaller problems we have decomposed to. If we look at baking cake, for example, we can find patterns within the smaller problems too. Let's see the example we have taken. Each cake will need a precise quantity of specific ingredients. Each ingredient needs identifying the name of the ingredient or the specific measurement. So the ingredients is one of the smaller problem, but this smaller problem as well needs more specifics, which identifying the ingredient name and the measurement of this ingredient. So once we know how to identify each ingredient and its amount, we can apply that pattern to all ingredients. So both patterns among the problems or within problems is all called specifics, which in sometimes it's not important, it's irrelevant, and we just might ignore. Alright, so the third key concept here is the abstraction. So why is actually the abstraction important? The abstraction allows us to actually create a general idea of what the problem is and how to solve it. For example, the process instructs us to remove all specific details. As we mentioned before, any specific that is not important, we just remove it because it's not going to help in the process. So any patterns that will not help us solve our problem, we just remove it. And this process help us to form our idea of the problem. This idea is known as model. Alright, so if we don't have abstract, we may end up with the wrong solution because so many specifics might lead us to the wrong way or to the wrong solution. Alright, so alright, let's go back to our cat example. If we didn't abstract, we might think that all cats have, for example, long hair, or all cats have the same eye color. So having abstracted, we know that although cats have tails and fur, Not all tails are long and not all fur is short. So in this case, abstraction has helped us to form a clearer model of cat. So abstraction is actually very important for us, help us to avoid any error or any to ignore any patterns that will not help us solve our real problem, and it might be a distraction after all. That's why abstraction is a very important process in TC concepts, key concepts. Okay, so there are actually, and talking about abstraction, there are general patterns and specific details. Let's see what are the differences between both of them. For example, when baking a cake, there are some general characteristics between cakes. For example, all cake needs ingredients. Each ingredient needs to be a specified quantity. All cake needs timing. All right, so when we actually abstract, we remove specific details and keep the general relevant patterns. This is very important. So when we abstract, we actually remove all specific details from here, and then we keep the general patterns that actually relevant to to solving the problem. Let's see examples. General patterns. We need to know that all cake has ingredients, but we don't actually need to know what those ingredients are. Okay. At the same time, general patterns, we need to know that each ingredient has a specified quantity, but we don't actually need to know what that quantity is as a specific details. We need to know each cake needs a specified time to bake, but we actually don't need to know how long this time is. Okay, so this is actually the difference between general patterns and specific details. We, once again, in our abstraction, we remove all specific details that are not or sorry, irrelevant to solving our problem. Okay, so abstraction, after all, help students learn to strip away complexity in order to reduce an artifact to its essence and still be able to know what the artifact is. To make you understand this, if you would ask your student to bake a cake, he would bake a cake, all right, knowing all the general patterns, but he doesn't actually need to know more specific details about baking cake process. Alright, so this is an example of abstraction. We could simply mention all the classes, all the phylums, or we could just say animal kingdom. So animal kingdom is actually consists of all phylums and classes. So the classification of animals is one example of abstraction. One more example of abstraction is Kuala Lumpur Rail Transit Network. We actually care about the general details. Okay, I am going to Ampang. I don't care what other stations in Ampang or where the location is, what they sell there. All these details, specific details, I don't care about. But the only thing that I care about is I'm going to Ampang, how to go there. This is my route. So this is actually the abstraction example. All right, so our last key concept here is algorithm. Algorithm is actually a step-by-step process to solve a small problem. So algorithm is a step-by-step process to solve our small problem. Algorithms actually underline the most basic tasks everyone engages in, from following a simple cooking recipe to providing a complicated driving directions. When you want to cook, for example, when you want to cook, you would follow a recipe, going from step by step, adding water, and then adding sugar, and then adding whatsoever. This is a step by step. It's called algorithm. Actually, the algorithm are very important to introduce students to algorithm by first using examples from their daily lives. You would, as a teacher, it's very important for you to introduce algorithm to your students and how they actually make use of it and how to link these algorithms to their daily lives. For example, in early grades, teachers could highlight the steps involved in brushing teeth, while in more advanced grades, students could engage in following steps during a lab experiment. So, once again, algorithm is a step-by-step process. You teach your early grades students how to brush their teeth, for example, step by step. This is the meaning of algorithm to them. How to use a lab, how to use the tools in a lab, how to put chemicals among each other. This is actually another example of using algorithms. All right. So algorithms actually needs to be presented using flowcharts. Flowcharts is actually charts that present all steps in your algorithm. So it's a diagram that represents a set of instructions. And it's normally used standard symbols to present different instructions. And we will see some examples in the following slides. So there are few real rules about the level of detail needed in a flowchart, and sometimes flowcharts are broken down into many steps to provide a lot of details about exactly what is happening. And sometimes they are simplified so that a number of steps occur in just one step. So a flowchart is actually a very detailed diagram that represent all instructions in your algorithm. Here, as we can see, there are two flowcharts here as an example for algorithm. Let's take this yellow flowchart as an example. Okay, we need to start with a start first, and then let's see, we want to order burger, all right? And then what's next? Next is, okay, do you want fries? If yes, okay, then order fries. If no, then they will ask you again, do you want a drink? If yes, okay, order drink. If no, then all right, just pay only for the burger and then end. So it's a very detailed process. We need to start, all right, and then if you want to order burger, if you want to add fries, sorry, and then yes, then you order. If not, you go directly down. All right, one more question. Do you want to drink? If yes, then ordering. If no, then you go directly pay only for. If no, you are going to pay only for the burger. All right. But if yes, you are going to pay for everything you have ordered. And then this is the end. This is an example for a flow chart. And this is all right, guys. This is the end of this class. Hope you enjoyed it, and we'll see you guys in the online session, so that we will have more time to discuss about the concept of TC. Please subscribe for this channel, because I'm going to upload all classes in this channel. And please take care, and bye bye.